give you co-host permissions.
Thank you.
Who else is supposed to be presenting?
Me as well.
I guess I can also do that now since if I'm co-host now.
Oh, you, yeah.
I'm connecting.
Oh, yeah, so not. Okay.
Got it.
Okay, so I think you're doing second one.
Thank you.
Thank you very much.
Yeah, I can see you. Let me see your screen. No, you haven't shared screen yet.
No, I haven't checked.
Yeah,
Share screen.
people.
Yeah.
Reasonable people as well.
I'm going to share stuff too. Okay. Okay, I guess I'll start now. So hi everyone. I hope you can hear me well online. And you can see my slides. So today we're going to talk about MetaCoq. So this is a MetaCoq tutorial, but first I'm going to explain quickly, and I'm going to give an introduction to what MetaCoq is and what we're going to do for this tutorial. Okay, so MetaCoq basically is Coq inside Coq. So here you have the MetaCoq logo and on. Okay. Oh, it's back. Okay. Which I represented in Coq. Okay. So you have a way to manipulate the syntax of Coq, and then because of that, you can write metaprogramming. So this is going to be the main focus of the tutorial, but there's another aspect of MetaCoq, which is the ability to reason about like the semantics of the language. So for instance, typing. And that allows you to write certified meta programs, like you can write a plugin and you certify it. So how does it work like broadly, but don't worry, we're going to go into more details later. Okay. Do I have to hold it somehow? Sorry for that. Okay. So you can see MetaCoq as a library, as a Coq library, in which you have a representation of terms, of Coq terms inside it. So you have this inductive type, a Coq inductive type, which has, can someone of you allow people in the room?
Yes. No, I think.
Are you co-hosts or?
No, we're not.
None of you are co-hosts?
I don't think.
I'm in the room in a second.
I'm
you
in
have
the
to
room,
speak
but I'm
in,
not
then you can
co-host.
make me co-host.
And actually, I don't. Okay, so I have to add. Okay, I'm going to add you two, and then I cannot put you co-host.
Great. So just continue and I will look forward.
Yeah.
Right, yes. Okay, sorry for that. Right, so you have this type of this inductive type that represent the syntax of Coq. So you have, for instance, variables that we call TREL and application and so on. And then you also have a plugin, a Coq plugin that makes the connection between actual Coq terms and their representation. So for instance, if you write a lambda, then I'm also going to admit people, right? So if you write, for instance, the application of the identity function, then you can quote it to its syntax, so to its representation in Coq. So it's going to be like the app constructor, the lambda constructor, whatever. But you can also do the opposite. So you also have a function to go from the syntax to Coq terms. And if the Coq term is well formed and well typed, then it will actually output a new actual Coq term that you can use in your proofs. And we also have a representation of Coq commands. So for instance, you can write the TM definition foo 24, and that's what it's going to do if you run it, is the equivalent of writing definition foo : 24. So you have this representation of basically everything you can write by hand in Coq, and then you can run it to have it have real effects. Okay, but again, more details later. So what can you do with that? For instance, if you know AutoSubst, so AutoSubst is a tool to write syntax with binders and then derive automatically substitution and weakening for it. And there is AutoSubst 2 version that's written in MetaCoq. So that's the kind of thing you can do. But for now, I think it's not as powerful, as complete as the AutoSubst 2 OCaml or Haskell version. I know. But it's, I think, in work in progress. You can also, for instance, derive induction principle or derive the subterm relation for an inductive type. Or you can, for instance, do translations like parametricity translation. So MetaCoq is not the only way to write meta programs in Coq. You can use Coq-LP, you can use LTAC2 or even OCaml, but we're going to focus on MetaCoq, of course. And one of the advantages of that is that MetaCoq is just Coq, so you're just writing Coq programs. You can use your Coq libraries, anything to build your terms, and also you can prove things about it. So this is the certified metaprogramming part that's kind of unique to MetaCoq. Okay. So how do you do certified metaprogramming? So you have this representation of typing, of reduction, and of definitional equality. So you have these judgments that are also inductive typed, inductive predicates, and you can reason about them. So they're all defined and specified within the MetaCoq library. And for instance, you can prove that parametricity preserves typing. And if you have a parametricity plugin, then it's helpful because it's really easy to make mistakes in like handling variables. And one of the main examples that we think is cool with that is that we can also verify a type checker for Coq itself. Okay, this is something that we have done in the past. So just quickly, why would we want to do that? So in a sense, we have the Coq kernel on one side and then the ideal Coq or the ideal theory on the other side. We would like to connect them. But the ideal Coq is not really specified. I don't know if you've tried to find a specification for it, but I don't think you found it. All right, you have the reference manual, you have some papers, some theses, and they all cover different parts of the whole thing, but none of them really captures what Coq is, because it's also a moving target. So we try to fix what the theory of Coq is, and we call it Pickwick for, I don't know if the name changes over time, but polymorphic calculus of cumulative inductive constructions. No, it's not. Today it's not. Okay. And then thanks to MetaCoq, we can write a specification for Coq inside Coq. And then we can like verify the kernel. I mean, that's at least that's the ideal goal that we have. And the fact that Coq is a moving target is no longer a problem anymore because we can like make the two evolve at the same time. And one of the interests of that is that then we can, if we have the verified kernel, it means that we can move from the trusted core paradigm, so trusted code base, trusted computing base, to the trusted theory paradigm. And we can really do that because thanks to extraction, and also some of it is already verified also in MetaCoq. We can produce an external checker and then like independently check functions. Okay, just a disclaimer, this is still not the full theory of Coq, so we're missing a few things, but we're going to hear about that later as well. Okay, so we gave you this quick overview, but the goal of this tutorial is going to be also give you more information about the MetaCoq project so that you learn about it and maybe get involved, and also teach you how to write simple meta programs, and the exercises are going to be about that. So today you're going to have some overview of the MetaCoq formalizations, then some meta programming with the commands and the functions, and then the exercises. So some practical information. We hope that you have Coq installed. If you do not, then we recommend that you use the Coq platform to install everything. We suggest also Coq 8.17, but probably 16 or 18 should work as well. We have a dedicated thread on the Coq Solib, so you can join and also ask questions. Well, you also need MetaCoq and an editor for that, right? So the information is on the MetaCoq tutorial page. Yeah, you can look up, and of course we're here to help you. So Pickwick is made because Coq changes. So is there a way to relate Coq to Pickwick as well? I'd say ideally the two are supposed to converge at some point. That's I mean, we have something that's not really defined, and then we're going to well, we're giving a specification, so we're giving a definition to it, and the connection with the implementation is the part that says that it's in the end going to be Coq itself.
But formally, we have no way to say that Coq and Pickwick are the same thing, because
right,
we claim it is, but there's no way to state that.
Yeah.
And one day we can hope to replace the Coq kernel by the one we certified, but that's not really. I mean, we're very far from this.
Yeah. So any questions?
Maybe we can use this also to ask who has MetaCoq installed.
Right.
No, who doesn't have MetaCoq?
Yeah, not quite sure. Who doesn't have MetaCoq installed but wants to use it today? Good, perfect. So my suggestion would be that we use the break for this. It should be if you have who wants to have MetaCoq installed.
Can you turn your mic on?
Doesn't even have Coq installed. Yeah. Who doesn't even have Coq installed? So as long as you have Coq installed, it should be good. I have two versions. Perfect. Yeah. We said it. But okay, good. Then we use the break later to do that. It should be easy. Yeah. And I'm writing the answer in the chat. You have to look at it.
But I can't.
You can't make me post interesting.
Answer
it, yes.
Yep.
But as long as you're in the room, we try to tell you everything that's happening at the chat.
Indeed, and I can even. Is this better? Yes.
Do you have your sound on?
Do I have my?
Sound on, in case you have questions.
Well,
Yeah, now we do.
yes, it should be good. Hopefully. Okay. So yeah, sorry for the online people. So I'm going to present kind of a part of the library that's basically not about metaprogramming and ask questions. I'm probably not going to be monitoring the chat too closely, but I have people in the room that will do it for me. Okay, excellent. Okay, and so this is kind of only going to be an overview. I can't cover all of it in 45 minutes. It's a bit, oh, well, it's going to be back on. Yeah, so I'm going to cover kind of the basics that you need for the metaprogramming part. But there's a lot more to read about. All the library everything's on GitHub and so on, so you can explore that directly if you're very brave. Otherwise, we have a paper that's currently only on HAL. It's being reviewed, which also tries to cover everything and go maybe into a bit more of the detail, especially on the meta theory side. So you can also go read that. And as Theo said, there's also a stream on the Coq where you can always ask questions, and we're reasonably active on there, so you should get answers in a reasonable time if you want to know more. Okay. And so the first thing, so there's kind of the different pieces to MetaCoq. The one that I'm going to tell you most about today, because that's the one that's the most relevant for metaprogramming, is called TemplateCoq. It's the one basically where that's really where that's the target of quoting. So when you use these quoting functions, you get something in this TemplateCoq part of MetaCoq, and then that's where also you want to unquote things. And that is related to the other part that I'm going to go on later, but that's the one that's really relevant for the metaprogramming aspect. And basically, it's not exactly what's happening in the Coq kernel, but it aims to be very close to what's happening in the Coq kernel, especially the data types are pretty much mirroring as Coq definitions what's happening in a kernel of Coq. So if you've ever played a little bit with that, you will probably recognize a lot of familiar things. And the whole point is that, I mean, it's supposed to be able to translate back and forth between the two. So it's logical that they're very close. And that's most of the time I'm going to spend on explaining the main data structure. That's the one that you're going to have to manipulate if you want to write meta programs. And so you have a representation of Coq terms, of course, like proofs and types and all of that. Of context, so kind of the local context, the thing that you manipulate when you're doing proofs, when you put variables in, and etc. Of the global environment, so the thing that contains all the definitions, the inductive type declaration, and so on. The thing that you load whenever you like import a new file and so on. That's where everything lives, and also all kinds of things related to universes. And so I'm going to tell you a little bit also as well on the representation of universes, which is kind of a tricky part of this whole story. I'm probably not going to touch it too much because hopefully you won't have to play with that too much when you're metaprogramming. But just for the sake of kind of completeness, I'll explain a little bit what's happening there. Okay, and so the first thing, maybe probably the most interesting here are terms. So as Theo said, we have this kind of big inductive type that's representing basically what's happening in a kernel of Coq with like a lot of cases for each of the things that we have around. So we have these variable. It's a very simple first order representation. There's no like well scoped or fancy intrinsically well typed things or whatnot. It's a very bare bone, and it really corresponds directly to the OCaml code. So yeah, variables are just Brine representation. Nothing very fancy here. Maybe in the future we'll try to have a nicer interface, but for now it's just a very raw thing. These are other kind of variables. For these one is used for goals, and I don't think we have much support for it currently. Also, same goes for existential variables, so the thing that you get when you want to do unification and so on. You can still manipulate them, especially one very useful thing is you can kind of create a MetaCoq term with a hole and leave Coq to fill in the hole after unquoting. So that's a very useful feature if you want to kind of let Coq do the like filling in holes. But that's basically most of it. We don't have much meta theory of this. We don't have like formalized unification or anything. But it's still there in case you want to use it. This is for universes. So I'm going to tell you a bit more about this later, but we have this kind of type of sorts which represent all kind of things you can have in type or prop or set. And they're all kind of factored out into this one constructor. Yes. Yeah.
So that even as it translates to an even, and then tries to.
Yes. So I think there's a thing called hole in the template coq plugin, which is basically one of these EVA, and whenever you use it, like also when you write a term in MetaCoq like this, you use hole and you unquote it, then the type check, so the unquoted thing is going to run through the type checker,
Right.
and then the type checker is going to fill that hole for you. Yes, yes. So that's the usual way you access this EVA thing, at least if you from the point of view of metaprogramming. Yes. Yeah, that's another thing that's in the kernel of Coq. It's not that important. It's just a way to have. Sorry. Yes. To have type annotations on a term. So something like this saying that T should have type A. And it's just there because it's there in the kernel, but probably not very interesting for you. And then you get into the more interesting things. So this is like the lambda-calculus fragment. So this represents what we could write for all in Coq. So with a type and sorry, this would be A and this would be B. And all binders, like here, they store a bunch of information, things like names for printing, for instance, relevance that's used for sprop things. So a bunch of things in there. You don't really have to think about it too much. But whenever we have a binding position, we always will have some of these A names that is going to store this kind of binding information in one. So at the binding site and not at the variable site. So that's all variables will share this information. Okay, this is the lambda abstraction, not much. Oops, sorry, this should probably be a T here, but whatever, again, the binder information, the type, and the body. Let-in nodes, where you also have, this is going to be very annoying. Yes, so where you have an extra, so you have an extra definition for the variable. And application nodes, what's maybe a bit special here is that applications are directly n-ary. So in all of what we do, we always ensure that we have at most one of this application node with a list of all its arguments. So we maintain as an invariant that you never can have two nested T-app nodes, but that you always have all the arguments there. And that's on the kernel side, it's very important for efficiency reasons because you can easily get to the head of the whole application, like list of application, and that's very useful in a lot of settings. And we have it's not here, but we have a kind of a smart constructor that does the smashing different lists if it hides the right thing. So you probably don't want to access directly the T-app thing. There's a thing called mec-apps, I think, which does the maintaining of this invariant for you when you want to use applications, so that you don't have to think about it. Then there's a lot of constructors for global constants. So this one, for instance, is for something that has a definition or an axiom, and all of them look pretty much the same. You have this thing which identifies the constant. So this kernel is kind of a path to the definition in the global environment. And because we have this universe polymorphic things, so you can have definitions that have like this pre-next quantification on universes, where whenever you have one of this definition, you also need to give them an instance of universes to instantiate these polymorphic things. I'm going to tell a bit more about this later on, but yes, that's the idea. And the same goes for inductive types and inductive constructors. We just have slightly richer information here. So this thing contains not only the name that identifies the inductive type, but also information so this, we have mutual inductive types, so not just one, but multiple definitions correspond to the one kernel. And so we also have information to identify which one of these things in this mutual block inductive should refer to, but otherwise it's pretty much the same. And for constructors, we have an even extra information that identifies, so again, the inductive and also what constructor, like what's the number of the constructor in the constructor list for the inductive type. And typically, if you think of in the metaprogramming side, these things you'd probably want to like take your favorite inductive type, quote it, and then look at what it looks like in these things, and you can just copy that information or do whatever you want with it. But you don't have to usually generate that thing yourself by hand. You can use quoting to make it a bit easier. Then there's the very dreaded case constructor, which is kind of the one nasty beast of this whole thing. Because I mean, if you've ever tried to write fully explicit pattern matching in Coq, you know how terrible it is. But so basically, you have all the branches here. You have the discrimini, so the thing that is matched on. Yes. You have this thing contains all the information from the return clause. So the thing that tells what type of whole pattern matching should have. And this thing is binding a bunch of information from the type and the discrimini, which is also is like a context in here that contains all these binders. And this thing you probably won't have to touch it too much, but it contains a bunch of information about the pattern matching, like what's the inductive type at which the pattern matching happens, some universe information as well, and so on. Okay. There's the projection. So you have these primitive projections now for record types with italos. So there's also a node for that, which contains the term that is projected and then some information identifying which projection we're taking from the term. Representation for mutual fixed point and co-fixed point. So you have, again, as for inductive types, you also have kind of mutual fixed points and mutual co-fixed points. So here, this is really kind of a list of functions that can all call each other. So that's what this m-fixed point thing does. So there's a list of the bodies and of the types of each of the mutually defined functions. And then you have just for constructors, something that identifies which function in the mutual block we are currently referring to. So if you define mutually, say, I don't know, an even and odd function, then both of them will be in here, and then you'd have 0 or 1, depending on whether you're looking at the even or odd function currently. And the two are, I think the data types are exactly similar, only typing really changes between the two. And the last addition in Coq, you have these primitive data types. So if you want to do like kind of efficient computation, you can directly manipulate things like primitive integers, primitive floats, and primitive arrays. So they're also in there if you ever want to start playing with them. So yeah, this whole thing is, I mean, it's a very comprehensive, of course, because it has to represent everything that's happening inside of Coq. Probably when you're starting playing with metaprogramming, most of these cases you can ignore or just kind of treat in a kind of identity fashion and really mainly play with a few constructors that you're interested in. And for instance, in the metaprogramming code, we already have a few functions that kind of just do identity, except on a few cases that are of interest. That's the typical case that's the typical way you're going to maintain or to manipulate these things and not care too much about typically the primitive data types, probably, at least at first. Okay, and so for instance, here's if you have the identity function at nat, that's how it would look like. And again, I mean, it's a bit of a mouthful. So probably you don't want to write it like this, but you can use quotes a lot to typically generate these kind of things for you. That's much, much easier than trying to write it by hand. And especially if you quote something, it's going to do a lot of things about like kernel path names and universes and stuff that you don't have to worry about yourself, but you can just quote things and everything will be done for you. So yeah, that's the typical way to generate these things. Okay, and of course you have a bunch of operations on this. So you can do substitution. which is going to replace the right variable with the right thing. So it's kind of a fancy thing. So what this is doing, if you look at the signature, is going to take the term in which you want to substitute, is going to take a list of terms, so it's kind of a parallel substitution, substituting all variables with this list of things, and it takes an offset. So this thing will substitute variables starting from the variable I with the elements of the list. So it's going to substitute the I for the first thing in the list, the I plus 1 for the second one, and so on. But the one we use most of the time is this unary substitution, which is just replacing the one variable at position j with the term u, and especially when j is 0, that's the usual way you access it at top level. Also double-blind lifting, and if you've ever played with binder and thing, you've probably played with this, which is mostly useful to kind of when you're changing the context to ensure that your variable, so this is going to shift all variables by n, and typically used when you're moving from a context to a context extension, that you want to apply this to your term so that the variable reference is kept the right one. And there's also an equivalent of universe substitution because we also have universe variable, universe level, so that's thing you might encounter it at times. And yeah, it's kind of a similar thing, just replacing universe variable with a universe instance. I'm just including it here because we'll probably see it later on in the typing rules, but it's probably not something you'll have to play at least early on. Okay, so that's it for terms, and then of course we on these terms we built a bunch of data types, and the most important ones are these contexts and environments which store these as we work. So the local context usually write it gamma, and that's the thing that changes during type checking. So that's the thing where the binders for lambda abstraction, for products, and so on and so forth are going to go. So it's basically a list of these declarations, and the declaration takes some binary information, a type, and importantly, it also has optionally a body, and this is useful for let binders. So if you have a let binders and you extend the context with it, then you are going to get something with a sum with the body of the binder in the context, rather than just a variable with no reference. Which is maybe something that's not too common in like simple lambda-calculus things, but that's what we have here. So yeah, you have maybe to be a little bit careful about this. And we write it in like a SNOC fashion. So this would be gamma extended with an assumption, so something without a body. That's just a notation for it. Here extended with a definition, and this is for like context concatenation. And you'll probably see these things quite a bit around. Okay, so that's kind of the easy side of things. And then there's the nasty side, which is this global environment. So where you have all the previous definition, inductive types, constructors, and so on and so forth. That thing is kind of a bigger, more complicated thing. But basically what you have is, in this global environment, so you have some universe information containing all the kind of this big universe graph that contains all the universes that have been defined so far, and then the constraints that they should satisfy for the whole thing to be valid. The important bit is this yes. Is it with the HDMI? I don't think so. Okay, so the important thing is this declaration, which is a list of pairs of a name and then a declaration. So this is a name that identifies this declaration, and we ensure that all these names are non-conflicting. So we never have two definitions with the same name, and this is some stuff for primitive type, not very important. And each of this global declaration, it's either a constant declaration or a mutual inductive one. And yes, and so that's you're going to see both of these types lurking around. This one is kind of at any point, like if you're in a CoQ, file and you're somewhere between two definitions, and you have a global env, and if you're inside a definition, you're working in some of this thing extended with like local universe declaration. Again, that's for universe polymorphic things. So you have a bunch of level variables that you're going to bind at the end of the definition when you're abstracting over your thing. So that's not the difference between the two are not too important, but you're probably going to see both data types happening around, so that you're not too surprised. Yes, and so a definition entry in this global context is going to look something like this. So you have a type always for your new constant. You have an optional body. So if you have that body, then this is a definition. If you don't have that body, then this is an axiom or hypothesis or something like this. And again, you have some universe information. So for polymorphic definitions, you have this universe declaration. And to support S-prop, you have this relevance information. But that's not too important for you. The important thing that you're going to manipulate is probably these two things. And I will spare you the actual mutual inductive thing. There's a lot of things in there. You have like the type of everything, the bodies of everything, like all the constructors, and then a bunch of information, and so on and so forth. If you want to look into that thing, you should probably just use like coq about and search functions to kind of explore this data type. Yes.
So what is the global context that you
Yeah.
had before? So when I code something,
Yes.
some definition,
Yeah.
then do I give it a global context as well?
When you, sorry?
When I code a definition in coq, and
Yes.
it refers to some other definitions in the coq.
Yeah. It's going to be everything. Like whenever you write the definition keyword, is going to make a new entry in here.
Yeah, but then
Yes.
when I code, what do I get?
So you have these so you have MetaCoq commands that allow you to extend the context, the global context of coq with a new definition with something that you define in MetaCoq. So you give a MetaCoq term, you unquote it to a definition in coq that's going to extend the global context
The
of
question is
coq.
when you quote something, do you
Code,
get
not when you uncode.
Yes.
Sorry.
Essentially, you can choose. There's a command that gives you both the context and the thing, and only the thing for efficiency.
Yes. Sorry. Yeah. Okay. Yeah. But yeah, Yannick is going to tell you more about the quoting side of things later on. So yeah. So here, basically, I'm not talking at all about the quoting and unquoting things, how you make this interact with coq. I'm just talking about how the whole thing is represented, basically, inside of coq. Yeah. Okay, so yeah, but in general, I mean, when you want to learn more about these things, the usual way is to get into the right place and start using like about and search commands to kind of look at what's happening. That's how usually you do it. I know what I want to look at, and I just do a bunch of abouts. And then when I reach the stage where I have enough information, I stop caring about the sub things, and I just do my work here. So yeah, that's the usual way to work with these things. And the last thing, I'm not going to go about it too much, is universes, just to have an idea what's happening under the hood. So kind of the most bare bone representation that we have is these levels. So if you've ever played with universes in coq, you know that there's basically three kind of things. I'm not talking about prop and S-prop, but just kind of at the type level. You have set, which is kind of representing the lowest level of type. Then you have these global levels, so things that are like kind of common to all the definitions, and they're identified by a string. And then you also have kind of these local level for this newer universe polymorphic thing. So this is kind of in a de Bruijn fashion, and this is local to the definition. Once you finish a definition, these are going to be abstracted away. And these are the things that you're going to need to instantiate with an instance later on, whenever you want to use that definition. And then the slightly higher thing is we're going to pair one of these things with a natural number, which is going to represent an offset. So for instance, if you have a pair of level 0 and a natural 2, this is going to represent like set, something that is like at least 2 levels higher than set. That you are able to talk about like a hierarchy a little bit. And then a sort is going to represent it either prop or S-prop, so these are just fixed, or it's type with a set of these expressions, which represents the max of all the things that are in the set. So if you've ever played with universes, you have like this max of a bunch of things, and that's how it's represented. In reality, there's a little bit of indirection, so these data types are not exactly like this, but that's basically the idea. And we're using these sets libraries to have efficient implementations because these things can get quite big. So we're using these things to get a bit faster there. And so again, you're probably not going to have to play with that too much. You can get away with quoting and unquoting to kind of propagate things around, but not write them down yourself. But for instance, so the prop would be represented as this thing, and sets would be something like this. So the type with a singleton with just the level 0. And then you also have constraints between these things, which represent what like when you're type checking these things in a universe hierarchy, you gather a bunch of constraints on how these universes should arrange with each other. So we also have data types that represent these things. And usually you have kind of a lot of accessor functions. So you probably don't have to, again, manipulate these things yourself. You just need to use this function that they typically, for instance, 2 sorts, a constraint, and then I'm going to tell you whether an equation between the 2 sorts in these constraint set is satisfied or not. So, and there's a bunch of these things between different sorts and universes for all the data types, but they all kind of have the same fashion of like, take a constraint set, the 2 things you want to compare, and then say whether or not they are indeed related. And that's something that you're probably going to use as well. From one of these global environments, there's a coercion that gets you the constraint sets corresponding to all the levels that are defined there and all the constraints between them. So typically, for instance, this function, you can give it a global environment and 2 sorts, and going to tell you in the current kind of global environment whether 2 things are related or not. And that's the main way we're going to use these things in typing, for instance. Yes, and so that's just so every declaration is going to be done in one of these universe declarations. So it either is just a monomorphic declaration, so there's nothing happening, or it's a polymorphic one, and so there you have a list of names in one of these constraints between the things. And when you want to use one of these polymorphic definitions, you're going to give a list of levels to instantiate all the things that were bound here, basically. And then you're going to have to check that these levels indeed satisfy the constraints. Okay, so that's it for the data types. I'm going to go a bit over the other things that we've formalized in there that you probably won't have to manipulate that much if you're just interested about manipulating terms. But that's something you should keep in mind because, of course, you want your thing to be well typed. So the first thing is reduction, which you're probably familiar with if you use like simple and things, these kind of tactics in Coq. So you have beta reduction, the usual one from the lambda-calculus. If you have a let binder, so this is an inductive relation between 2 terms in the global context and a local one. And this is saying that the left term reduces the right term. So if you, for instance, application of a lambda abstraction reduces to a substitution in the right thing. You can reduce Latin binders, again, to a substitution. If you have a variable which corresponds to something that is defined in the context, then you can also reduce the variable to the body of the definition. And you can do the same for global definitions. So if you have a constant that's defined to be some body, then you can also obtain the substituted body with the right universes. Reducing of fix and cofix point when they are in the right situation. You just kind of unfold the thing to the right function and apply to the right arguments. And projections as well when they're, so this is all fix and cofix, and they're only allowed whenever a fix is applied or when a cofix is forced, so by an outside case or projection. That's for termination. Pattern matching also reduces, and I'm not going to tell you what w.r.t does, but it does what you think. So selects the right branch, substituted what needs to be substituted in the branch, and gives you that. Projections as well reduce when you have a projection of a constructor. You get the relevant argument. And then this whole thing is closed by congruence. It can reduce under any, like in the left or right side of an application, for instance. And from this definition, we define cumulativity, so how we compare typically types when we're in typing. So this is basically the least relation that's both a congruence, that's sorry, I wrote equivalence, but it's rather, it's not symmetric because it's kind of a pre-order between things because of like universe levels. So for instance, prop would be a subtype, say, of set. And so, but not the other way around. It contains reduction, and the important thing is that it's cumulative. So whenever a sort is smaller than another one, then you get this pre-order thing between the two corresponding constructors. So it's a kind of a weak form of subtyping, if you wish, that basically has this universe thing as a base case. And you can go look up in the formalization what it looks like. And basically we have two ways to write this down, either directly as an inductive relation, so you have just everything spelled out, or in a more algorithmic way where you go through reduction to things that are equal up to universes using this like LQ term from before. And then we show later on that these two things actually coincide. And the last thing that you probably is a little bit important here is typing, of course. So again, it's an inductive relation between a term and its type in a global environment and a context. And this is probably not too surprising if you've played with Coq before. So for instance, the variable is going to have the right type obtained from the context. Sorts, we have these accessor to give you what's the kind of next level of a sort should be. That's going to do all the manipulation of the like universe indices and so on, so that you don't have to do it yourself. Yes, lambda abstraction. So if you have a type and the thing that has the right type in the extended context, and you get the lambda abstraction. Yes, so as I said, application is n-ary. So we have this constraint that the head of an application should not be itself an application. That's the invariant I was saying earlier about maintaining this list information. And the kind of the simpler version of it that doesn't use this fancy thing for typing the whole list at the same time is the one that you'd expect from lambda-calculus or dependent type systems. Yes, so for constants, for instance, you grab them in the global. So you have these things to tell that something is declared properly in the global context and has a certain declaration, and then you instantiate it with the universe that should be well formed. And there's a bunch more of this for the other things. The conversion, that's the use of cumulativity here. If you have any term with a given type, that's a valid type, and the B is larger than A, then you can also assign the type B to T. So really subtyping, the usual subtyping rule. Yeah, probably you don't want to understand that live now. We have a typing rule for case. It's a bit messy. If you kind of take your time and go through it, it's not that bad. It's just a bit of a mouthful, and the simplified version for projections. Same for fix and the other things. I mean, again, you should probably just kind of go through it slowly, maybe unfolding the right thing when you want, using search commands or about commands to kind of understand what's happening if you really want to manipulate these things. But if you're used to Coq, it's not very surprising. I mean, if you ever try to type check your own terms in Coq, then all these things are going to be quite familiar to you at the end of the day. And I'm not going to inflict you the global environment typing judgment, because that's even worse. But basically, so as I said, all these kernel names should be unique to refer to things in a non-ambiguous way. All the like bodies, types, everything should be well typed. And then we have extra conditions for inductive types. So these positivity conditions. So we don't have general recursive types. We only have these kind of positive inductive types. So you can only refer to the inductive type itself in the right positions, so that we know that the thing has an initial algebra in the semantics. There's a bunch of things to handle cumulative universes, and there's this constraint in Coq that you cannot eliminate inductive types from prop into type when there are multiple cases to maintain a proof irrelevance. So we also have this allowed elimination bit that tells you whether or not you are allowed to eliminate. I mean, how you are allowed to use a pattern matching on the inductive type that's defined to create relevant data. And again, use search commands to kind of look at these things in more detail. Okay, so that's mostly it for the things that you will have to play with coding, probably. now I'm going to tell you a bit more about all the things that we've mechanized and formalized, the properties of these things. That's less relevant for meta programming, but there's quite a lot of work that happened there. So most of the work we've done is actually not on TutorialFest. So okay. So TutorialFest is the thing that you get directly when you quote Coq terms, and then when you can unquote back. But that thing contains a lot of very nasty things, like for instance, the cast nodes that are there because they're there in Coq, but they're not very relevant for meta theory because they're not doing much. NRE application is really a pain when you want to develop meta theory. So we have this Pickwick language, which is very similar to TutorialFest, but slightly simplified, so that it's easier to work on it. And then we have proofs that basically these two things are equivalent, so you can translate back and forth and in a typing preserving way. So this is really just a simplification for meta theory, but everything that we show here can be kind of transported back here. And we have a lot of meta theoretical work on Pickwick. So the substitution property with a bunch of substitution calculus and then universe substitution as well, and we show that everything is respected in the right way. So typing is preserved by substitution. Kind of the big property where we have to work a little bit is to show confluence of this reduction relation using kind of standard technique from lambda-calculus, the Tate-Martinov confluence proof, and also a simulation. So if you have two things that are related with this, like they're the same up to universes, and you reduce on one side, then you can map it with a similar reduction on the other side. And using these two things together, you can get a lot of properties on how conversion behaves and so on. And kind of maybe the biggest one is we have subject reduction for this thing, which is, I mean, the proof is not very surprising. It's just very large and complicated because, I mean, you have match and all these nasty things. But there's it's a kind of relatively standard proof. And if you've ever played with meta theory of dependent type systems, you know that people care a lot about normalization. And here we do not try to prove it. Part of the reason is that due to this guy, you can't really show consistency of Coq inside of Coq itself, and normalization would let us derive consistency. So for just like logical limitations, we can't really try and prove normalization. And also it would just be very, very hard. So we haven't really looked at it too much. So basically it's axiomatized. So we have this ground condition. So in what ensures termination of Coq definition, especially the definition by fixed points, is this guard condition that tells you can only do recursive calls on structural subterms. And that's ensured by these guard conditions. So what we do is we axiomatize the existence of such a guard condition. And then we axiomatize the fact that under this assumption, every well-typed term is normalizing. This is kind of a fancy constructive way of phrasing it. But yeah, all of this is kind of axiomatized. And so in principle, we could have different guards as long as they satisfy this axiom, we would be fine. So yeah, and we don't use that too much for proofs. It's mostly used later on when we implement a type checker, we need a termination argument for it, and that's where we really need to code normalization. But for instance, subject reduction or the substitution properties do not rely; they're completely axiom free. They don't rely on any of these axioms. Okay, and the last bit of Pickwick that lets us obtain a safe checker at the end of the day. Okay, is these algorithmic judgments. So I've talked a little bit about the fact we have like these two presentations for cumulativity. We have kind of the declarative one and one that's based on reduction. And for typing, we also have two presentations. We have again kind of the declarative one, we can do cumulativity anywhere, and we have a bidirectional presentation that's kind of much more constrained and term directed. And we show that these algorithmic presentations are equivalent to the declarative presentation. That's kind of the spec, say, of Pickwick. And then we can use that to then show that the safe checker is sound and complete, because this thing is very close to what's actually happening in what we've implemented. there's a nice story there. We actually found a bug in Coq while doing this equivalence proof. So it's actually quite informative to try and play with these things really in the kind of the dirty details. But yes, and all of this is formalized and action-free. I mean, at least this equivalence here, and this one, of course, the state checker to be defined needs normalization. So yeah.
So what was the bug in the Coq?
Yes. So basically, we started trying to prove completeness of the algorithm presentation with respect to Pickwick. And at some point, I went to Matthieu and said, there's something weird happening with pattern matching and polymorphic universes. He looked at it very hard, hacked in Coq for 5 minutes, and then found a bug that was also affecting Coq. So basically, we had translated literally what was happening in the Coq checker in MetaCoq. And then by doing the formalization there, we found a bug that was also present in the kernel itself.
Okay, there was a bug in checking utility conditions.
Yes, on like the context for the predicate in pattern matching nodes. Yes.
Not an inconsistency.
It wasn't so. Yeah. So in fact, it was an incompleteness issue. So this manifested as a subject reduction. So something would type check, you would evaluate it, and then the result of evaluation would not type check anymore because it would be typable in a theory, but the checker would not be able to find it because of the completeness problem. But it was not affecting soundness. You could not use this to prove false. You just had sec false. So, I mean, or like weird anomaly reporting. So still not ideal, but no proof of false. Actually.
Meven,
Yes.
if you increase subject reduction, you can break it with conductive.
Yes.
Here it's in the experimentation of the w.r.t checker that we will do that?
Yes. So no, sorry. So so we have the conference proof. It handles also the positive cofix, the one that don't have subject reduction. But we have a flag that we can turn on and off to say whether or not these things are typable, and the subject reduction is done in case the flag is turned on. So I mean, so like the thing are not typable. Yes. So subject reduction only holds if you can't type these things that we know won't work. Yeah.
How critical
handles them?
Question. How critical is the assumption of normalization to the consistency argument?
So we only derive consistency from the normalization proof. We don't try to prove consistency at all without it. So I mean, consistency is just kind of an easy consequence of normalization and like subject reduction and all the other things that we've proven.
But if you didn't assume normalization, like if Coq turns out not to be normalizing in some weird edge case,
yeah,
how would that destroy the consistency proof, or is there another route to the consistency proof that doesn't go?
No, there is no other route. Like the only way we know how to prove consistency for these things, or we could be theoretic models or things like that, but like we don't even try to build any relation to semantics from this thing. So we could, but we are not. Yes. So the only way we know how to derive consistency here is through normalization. So if you don't assume normalization, you don't know that the thing is consistent. But in some way, we don't care that much about consistency. What we care about is to get a certified type checker at the end of the day, and that thing only relies on normalization for its termination. But the whole equivalence between the declarative presentation and the algorithmic one, this one is completely action-free. So we at least know that the type checker is doing something relatively sane, even in the absence of normalization. We don't know whether it's terminating or not, but it's still doing something sensible, even if normalization turned out to be false.
It's not that we don't care about consistency, it's that it's not the aim of the method.
Yeah, I mean, okay, yeah, of course we care about consistency. Yeah, okay, maybe it's a better way to phrase it. I mean, of course we care about consistency, and if we were able to prove normalization, all of us would be very happy, I think. And if you want to hear a bit more about this, there's also have a presentation at CPV actually on Tuesday on these kind of things. But currently, it's very much out of reach to prove normalization for Pickwick. So that's kind of a trade-off. Say we want to look at the real system. We don't really know how to prove normalization for it. So for now, we assume it, and at least we know exactly what we want to have. And maybe later on, someone can come and fill in the axiomatic gap.
Pickwick is a bit overloaded. You know, the Pickwick that you're formalized in Coq or the Pickwick that is on paper?
I mean the one that's in MetaCoq. Yes. Yeah. Yes. Yes. So at the end of the day, you get a proper type checking function you don't want to execute that inside of Coq because it's doing a bunch of computation of accessibility proofs and so on. But then you can extract this and you can run this.
You can.
You can, oh yes,
Might
because
not want to, but you
Gontier
can.
strict, but you probably don't want to, but you can execute a little bit inside of Coq using like accessibility fueling. But the idea is that you want to extract that thing, and then you get a proper checking function with the actual type that you want, that's going to erase all the like well formation assumption and so on, and actually run in a vaguely efficient way. Yeah, and you can use that thing through the MetaCoq commands. Actually, give you access to this certified checker if you want to use it. Okay, and I'm going to go quick about this because I'm starting to be over time. But there's also work on certifying erasure and extraction. So if you've ever played with extraction in Coq, there's basically kind of two aspects to it. There's this erasure path that takes in Coq terms and erases everything that has to do with proofs and types to obtain something that's kind of only contains the interesting computational content. So you get to something that's this lambda box language is basically the same, except it has this extra construct that represents everything that you want to erase. And so we have an erasure procedure that takes in a term and then returns something in this thing, and that is basically going to kind of look at whether something is a proposition or not, and depending on that, is going to erase the relevant bits. And then from this extracted lambda box thing, you can generate like OCaml code or something, and you can talk with Yannick about this. He's the expert here. But there's a bunch of like a complicated pipeline to do all of this, and most of this is certified now, and they have a draft paper that's coming up on these things. So yeah, that's also part of the thing, and the idea is that, of course, if we want to obtain a certified extracted checker out of the thing that we've done in MetaCoq, it's nice to also have certified this thing because now we know we can trust also the thing that produces the OCaml code from the Coq code. And there's a lot more to come. I mean, this is kind of the current state of things, but there's a lot of active work on the meta-theoretic side. So, I mean, of course, we're not exactly happy about normalization in the GANs, so there's this extra work on trying to like give instances of the GAN and maybe try and prove normalization for some of the things. And we're missing a few things. That's kind of the sad part of the story, is that these things are what's in Coq and that we don't support in MetaCoq yet. So our pquick is not exactly as expressive currently as what Coq kernels allow. And these are basically the three things that are missing. And well, we're working on them, and hopefully we'll get something that is as expressive as the Coq kernel in a reasonable time frame. But yeah, it's still in progress. And I think that's it for me. If you have extra question, now's the moment, and otherwise I'll hand in to Yannick for the meta-programming part of things. Yes.
You actually taken some proofs from and transform them to your quick kernel inside MetaCoq.
So you mean like taking terms that have been type checked in Coq and then yes, and but the thing is that especially because we're missing Italos, a lot of the things that type check in Coq actually use these, and so we're not able to type check kind of actual big libraries. But on like small examples, yes, you can.
You expect that in the future you will be able to, for example,
that's the
arithmetic library. And
yes, that's basically kind of the long-term goal is to get something like Coq check. So probably our certified checker is never going to be as fast as the Coq kernel. So hopefully we can get something like an external checker that you can run once in a while, once you're happy with your formalization, and then make extra sure that what you've done is actually correct. That's kind of the idea.
Then there is some way to get some kind of reflection principle in both directions to obtain type check with one and get a proof of checking in the other or something like that.
So the thing is that in the end, all these things, they're just like OCaml functions. So you can't really get any soundness thing. So you just have to kind of trust that if the certified one said yes, then the kernel would have said yes as well or something like this. But you can't really prove this because I mean the whole point is that the actual kernel, the current one, is just OCaml code, so we don't really have any guarantees on what it's actually doing. But the point is that the thing that we're implementing is really close to that kernel. And I mean that's why we were able to find bugs in the actual Coq kernel by looking at how that we were doing. So I mean the two are really similar. So hopefully anything we see on one side should be also happening on the other. And it's just like an efficiency concern that they want to run the OCaml one further extracted. Yes.
So I must get this correctly. You don't have some OCaml semantics that you use to sort of verify the equivalence that you show.
You mean between our extracted kernel and or between what things?
Essentially between quick and the actual Coq.
No. So basically, the relation between the actual Coq kernel and the certified checker we have is look at them hard and see their privacy. But that's the only thing we can really do. Yeah. And yeah, maybe if we had like like semantics for OCaml and so on, we might try and actually relate the two. Probably the saner way would be to just like take our certified thing and then make it faster by adding some of the optimization that are in a Coq kernel. It would probably be the better way to do. And one other thing that I haven't really said is that we have tried to design the type checker in kind of a modular way so that, for instance, you can plug the fast universe like constraint verification that is part of the kernel inside our certified checker. Because basically, if you try to use our certified universe verification, it doesn't scale very well because it's a relatively naive algorithm compared to what's implemented in the kernel. But you can use our certified checker using that thing as a subroutine if you want to have like fast universe checking, but still the certified checker. So that's also one hope in the future, is that we can maybe have like kind of all these moving pieces and plug in and out the certified bits or the fast bits at will. Yeah. You good to go?
You haven't joined audio.
Need to turn on the mic. Okay.
Yes.
So,
No more online things.
Yeah, and you,
Where's my Zoom?
you closed your laptop, so I had to switch.
Oh, sorry, I didn't think about this.
No. Joining now. All right, good. Then we are back for a quick 15 minutes introduction of the thing we call the template monad, and I'm going to explain what that is. Then we're going to take the break, fix the HDMI issue, this one. And then we're going to do real meta programming and do the things you would like to do to write plugins or tactics in MetaCoq instead of using something like OCaml or LTAC or whatever. All right. This one is the quick part that is more or less about doing things like the commands that you can do in Coq. You have commands like check or compute or about or definition and these kinds of things, which deal with the global environment, which check a term, which compute the normal form of a term, which find out where something is defined, which add the definition to the global environment. All of these things you can do live in Coq. You sometimes want to do in a more maybe programmatic way where you want to combine different of these things. So in particular, one thing MetaCoq does, and it does other things that we're going to talk about later, one thing MetaCoq does is it gives us the possibility to actually run all of these commands through a more computational interface. You can write programs that run some of these commands. And I think they are all in a type called template monad. Perfect. Indeed. And I can jump to the definition and I can zoom out a little bit. In particular, you have a monad of these programs that can interact with the global environment. And often that's actually enough to write interesting things. So you can do stuff like you can, well, it's a monad, so you can return so if the online people are irritated what's happening when the speaker is just freezing for 3 or 4 seconds, that's because our screen in the room sometimes goes black for 3 or 4 seconds. And we agreed with the audio video chess that for now we just freeze when that happens. And then we continue for the second half of the tutorial. They might be able to fix that. Good. So it's a monad you can return and bind. That's not so interesting. You can print definitions. You can send messages to the user. You can fail. Yeah. Sorry. Better. People in the last row. Good. Perfect. All right. Going to say the same things again. So it's a monad. You can return something. You can bind something. You can print terms. You can send messages to the user. You can fail. You can evaluate a certain thing according to a certain reduction strategy. You can do CBN, CBV, whatever, if you know how these kinds of things. You can define, you can add a definition to the global environment by giving it doesn't make sense to talk about it when you don't see it. So yeah, there we go. By giving an identifier, maybe a reduction strategy, and something you want to add to the global environment under this identifier. There's also the possibility to add axioms or to do a lemma, which is then going to open proof mode to fill the body of the lemma. I'm going over this quickly because one, you don't need it for the exercises later. In the exercise, we're staying in a kind of pure fragment where you don't interact with the global environment. So I just want to mention the bits and pieces that you could do in case that you ever kind of think about how can I solve my problem. I want to mention different things that you could solve using MetaCoq, but we're not going to go into a lot of detail. You can do other things that you can do in LTAC, like generate a fresh name, locate a definition. You can quote a term on the fly to get its representation, then analyze its representation a bit, and then unquote again. You can add instances to the instance database of type class search. You can also ask type class search to find an instance for you. These kinds of things that you would normally have to do manually, you can do programmatically writing template monad programs. Okay, and now we can vary. Yes, I would like to see what I was planning to do with you on my screen here. Perfect. And then on this screen, I'm going to do it. Perfect. All right. We can look a little bit into the part of quoting and unquoting that Meven already mentioned, and then write one or two very simple monadic template programs that interact with the environment, just so you see it. And then in the second part, we switch to actually writing nice plugins in Coq that are a bit tricky to write maybe in other meta programming languages. So again, we will be working with respect to this definition of terms that more or less resemble the OCaml definition of terms that you have in the kernel. So you're going to have variables, EVAs, application, and so on, exactly the data type Meven showed you. And then there are two ways to actually see. You might have to increase the font size again. Okay, thank you. Good. So you can either run the command MetaCoq quote and then put the Coq term there to let MetaCoq test quote to let Coq output exactly the representation in this inductive type for you. So this says that the function that takes an x as an argument of type natural numbers and then x is going to be a lambda, which has a relevant binder with name x. And then it takes as the type is going to be an inductive type that is saved in a global context under this way. And it's the 0th inductive type in this mutual inductive block, because actually natural numbers are not interestingly mutual inductive. And then it's just going to be the 0th de Bruijn index. So the first thing that's returned. If this would take a second argument, then it would still be a lambda x, natural numbers, lambda y, booleans, and then it's going to be TRL1 because you have to jump. Perfect. In the context, so this is how MetaCoq does it. When you later do the exercises, you get a little prelude file which gives you a bit of nicer syntax. Then you can write check quote, and then this thing here, which I think should do the same thing. Yeah. So you can kind of inline write quote and then get the quotation of a closed term, which is going to make some things easier. Yes. So I'm not going to tell you what it, yes, in the essence, it's exactly this. It's kind of hooking into OCaml plugin that then quotes on the fly, and it's implemented maybe in a hacky way that's not exactly this, but you can think of it as exactly that. And you can also, I mean, we can this now really lives in the term language, so I can even write definition T is this, and then I can print the definition T, and it's now going to contain exactly the syntax. But yes, it's kind of a hook to the global environment, saying like now run some OCaml code, get something out of the kernel, put it here, and then continue evaluating. Yeah, and of course you can also go the other way. You can also unquote things. That's what Meven also already mentioned. So for instance, I think I should be able to write unquote T now. And now it's going to exactly, so T is containing the syntax. And if I do unquote T, it's exactly going back to this term here now. All right. Oop. Good.
And it's type checked on the fly.
And it's type checked on the fly. If it doesn't type check, it doesn't work. Yes. Yeah, but Thomas is working on a mode where you can also write non-well-typed terms there, because in LTAC you have a mode where you can write non-well-typed terms, and sometimes you might want to write non-well-typed terms and might want to go both ways, and I think he's very far in this. Yeah. Awesome, good. So let me see. Then we're going to run a couple of simple commands through the monad. Come on.
It's back.
Good. There we go. We're going to run a couple of simple commands through the monad. For instance, we can do a thing where, yes, let's write a simple print inductive command that you give a name, and then it's going to print the definition of the inductive data type, and it's going to give you, we want it to print, but first it's going to give you a representation of this inductive data type, so you can analyze how many constructors it has, these kinds of things. And then we're going to print it out as this little exercise. So we're going to write a definition print inductive, which is going to take as argument a quality, which I think is just probably just equivalent to string. Yes, actually, let's say we take a string, and then we are morally, what you want to do is we want to locate this definition to find it somewhere, and then we want to access it, and then we want to see what's in this definition. And this is going to be a template program, so it's going to be live in the template monad, and we don't want to return anything interesting because we're going to print it. And then whenever you have something of this template monad thing, we can later write MetaCoq run something like print inductive nat. And that's going to exactly print then the definition of the inductive data type now. But whenever you have a template monadic, I just pretend it's there. Whenever you have a template monadic program, and then you can later run it with this command to interact with the environment. So this is the syntax of saying how you want to interact with the environment, and then you use run to actually run in the environment. Perfect. Also, people in the last row, when I'm too low on the screen, if you wave to me, I know that this means I'm too low on the screen and you cannot see anything anymore. So feel free to wave, and then I will try to scroll. Also, yeah, I will try. Good. You can also move your head left to right, and I also get the idea. But if you wave, it works better. Good. So what I want to do, even though you don't see it, I first want to locate. Yep, close. I want to locate Q. So I'm going to say locate the string Q and actually find out what this thing stands for. And why not? We can also do something like tm print kn, and probably that has the wrong type. Nope, it has the right type. So for starters, we're going to do this. We're going to locate the thing, and then we're going to print the information that was located. So if we run this now, it is now going to tell you actually nat is a reference to an inductive, and this inductive lives in here, and it's the 0th inductive living in here. So in particular, we want to get out this information in the thing, namely the path, and then we want to access the constant at this path to look at it. There we go. There we go. So we know that what's going to go back, what's going to come back is going to be an int ref. that contains some inductive information. In the case where it's not an in-graph, so it might be, for instance, a reference to a global constant we want to fail. Yeah.
There's a question you ask is there's a Unicode, so like the user say, oh,
no. Which part here is not ASCII?
Yes,
that's good.
I mean, it's just that you have
Yeah, I have prettifications. I'm sorry, I have prettification turned on, so I don't know how to turn it off. Maybe we fix it for the second half. So you have an inductive, you have a reference to an inductive, and this in thing is going to contain exactly the path at the moment. And then what we want to do is there is a command that can quote an inductive to get its what's happening? An inductive to get its representation, where we can give this field, where are we? This field of the int field, let me see. There we go. Where yes, inductive int, there we go. I have what? Ah, yeah, perfect, thank you. Inductive int, which is going to return now the representation, and then we want to print it. So some monadic notation, again, it doesn't matter horribly much if you cannot remember this, because this is just a little example what one could do. Good. And now if I run that, it is hopefully going to print me exactly all of the information that we got. So I located the thing to got the expanded name, and then I looked it up in the global environment and quoted the thing to get exactly the representation in the kernel, which has all of the information about the inductive, which tells us that this is a finite inductive type, more or less, that I think just says it's inductive and not co-inductive. It does not have any parameters, thus I don't have a context of the types of the parameters. It has exactly one body, which is called nat. It does not have any indices. It lives in the lowest universe level sort. Its type thus is, its type is this, its sort is that. We can eliminate into any other inductive type. There are no restrictions on eliminations. There are two constructors. One of them is named O, which has no arguments, no indices, and exactly has the type relative 0. So that means it's exactly the one I'm currently defining, so natural numbers. And it has arity 0, no arguments, once again. And then there's another constructor, which is called S, which as argument takes exactly one thing, which is TRL 0. So the thing we are defining, it takes a natural number. It has no indices. Its type is, well, what you would expect. And, well, that's it. And then it says also that inductive natural numbers are not polymorphic, and I don't know what the variance is doing, but yeah. Okay, yeah. Yeah, I think bifinite means you can treat it as both. I think something like Booleans are going to be.
It's the keyword variant, if you've ever seen that. Yeah.
Okay, but if you define Booleans, inductive bool, you're also going to get bifinite. Because it's
variance bool whatnot,
yeah,
it will be accepted and indeed
okay,
bifinite. If you inductive bool, probably not.
Okay. But morally, it's the things that can be both. Okay. So yes, perfect. It's exactly 10:30, and we're annoyed anyways by the screen turning off all the time. So you can write programs like this that interact with the environment, look things up, maybe do some more interesting things than just basing on whether this is an inductive reference. And now we're going to take a 30 minutes break. The people who want to install MetaCoq, please stay here. We will tell you roughly what to do. And then in the second part, we're going to write, we're going to do a little bit more of live coding here, we all together, and then you're going to write an exercise and implement something useful that was asked about on the Coq mailing list last week. And nobody had an answer, so you can solve this this week. Perfect. But 30 minutes break, and then we are back at 11. Sure. Good. I hope the video shares.
I put my slides.
Good. I think we are back. Is the font size big enough in the back row? Or does that work? Yeah, sure. Because it's, yes, there we go. That works, right? Okay, perfect. Also, for the online people and for the people in the room, we did not fix the video problem. So it will still go occasionally black. I will still occasionally freeze and just wait for it to come back. But it's only about 20-30 minutes of writing a little bit of meta programs where I write them and then you all write your meta programs and we should be fine again. Okay, I want to do two things. I think I want to do one easy reification exercise where we want something like we have an expression of actual natural numbers in Coq, so a Coq term like maybe this, and then we want to be able to quote this term, reify it, and then unquote the result in order to turn an expression over a natural number, like an arithmetic expression over natural numbers in Coq, into an expression over an inductive data type. So the usual thing in reification, reflection reification, where you have a reified version of the like sub language of Coq you care about, and you want to go from Coq to this inductive representation. So we want to write a function that inspects the syntax of things that more or less can contain applications of the plus function and maybe some natural numbers, and then translate the plus function to the plus in the inductive data type and the natural numbers to exactly the natural numbers in the data type. Easy exercise. You can easily do it in LTAC. People do it routinely in LTAC. Once you scale up, things become a bit tricky in LTAC. And in particular, what's very hard in LTAC is dealing with open things and binders. And that's exactly a thing MetaCoq can just do, because we have a representation of binders. Everything is there that you need. You might have to fiddle a bit to get the right information, but everything is around. This doesn't contain binders. It's an easy exercise, but this scales to something that works really well also in more general contexts. All right. So what we want to do is we want to write a function reify that takes as input syntax and produces as output syntax. In particular, that's going to be a completely pure Coq function that really takes the term representation in, the term representation out, and then we're using quote to actually get something into it, and we're using out quote to get something out of it. But we're doing a phase separation. We write a completely pure function working on syntax, and then we use MetaCoq's facilities to plug something in and get something out of it. So we are going to write the function reify, which takes as input a term and which produces a term. Terms are exactly the things we have seen before. And then more or less, there are two interesting cases. Either we are seeing the application of something to two arguments, match x with. Either we are seeing the application of something to two arguments, then we will have to do something. Or we are in another case, and we will have to do something. And more or less, we can assume that the other case is the case where we see a natural number, and this is the case where we have to figure out whether it's plus or not. Let's assume that. So what we can do here is we need to figure out whether this constant is exactly plus. So we can use a Boolean equality check on syntax, and we want to see whether C is exactly the representation of plus. So I can write it like this. And if that is the case, what we want to return is we want to return an application which in the head now has the A plus there. And we want to recursively reify U and reify V. Reify V. Okay. And if it's not the plus, then we want to treat the thing as a natural number constant. So we're going to return the application of the syntax of a const to exactly x. Okay, because it's already a natural number. So the typing should work reasonably well. We don't have to reify? Yes, exactly. Yeah. So from the type level, everything works. So we get in a term, we check whether the head is actually the quotation of plus. This gives us the syntax of plus. We don't actually have to read it, but it's going to compare to the right thing. And maybe let's try something here just to see that this type checks if you print the definition, you see that it actually unfolded. You see that it unfolded on the fly, my quotation to plus and quote to a plus to the right thing. But you don't have to remember what the quotation is. You can still write it here. At definition time, it is unfolded, so this Boolean check computes the right thing. And in the case here, we also want to return, say this is a constant, quote a const, and we want it to be applied to x. And I think that's already enough to run the simple example. I go a few from the beginning, where we want to reify the quotation of, let's say, 4 plus 3, or whatever. This. Cool. And it actually gives us, I think, the right thing here. Okay, but in principle, you can easily write functions that work on syntax and through quote and unquote come back and forth. You can embed this in your LTAG program, for instance, because it's just a function that has to be run. So it works in every context. Good. And I think as a second example, we are going to do a thing that's a tiny bit more interesting, right? Yes. Yes, yes. I'm going to do one where we also have to reduce terms and play a bit with the type checker to infer things. But again, I want to stay in the pure fragment of Coq, where I just write real Coq functions that work on the syntax and then glue this together with quote and unquote at the end to go back and forth with the kernel. And in general, that's a reasonable way of writing and defining things. So as long as you can stay in the pure fragment of Coq, where you just write Coq functions, because we all know how to write Coq functions, everything is very nice. You don't have to learn a new language. You don't have to learn any primitives. You just have to deal with all of these definitions. Maybe you have to check what their type is, and so on. But you can actually really write Coq programs to extend Coq with features. So I'm going to copy paste some things here. Up. I'm going to, and you don't have to look. I'm actually not showing you the definition of these things. We are going to use a reduce function, which essentially takes a global environment, a context, and a term, and then reduces to the normal form of this term. And we're going to use an infer type function, which takes a global environment, something here, I don't actually know what that is, a local context, a term, and then outputs some type information about the thing. Yep, exactly. And we're going to, these functions are purely implemented in Coq. Somebody wrote a type inference algorithm. Somebody wrote this reduction algorithm. I don't know who it was. Maybe you, Theo? No, I don't remember. Maybe Simon, long time ago. Yeah, but you can have these functions and they are pure Coq functions just doing exactly the thing you would expect them to do. And now we want to use them to implement the following automation. I copy paste this again. So I want to write a tactic. No, I want to write a plugin that takes as input a term. And then it's going to go through the term. It's going to look for constants in the term. And it's going to unfold all of them unless they are computationally irrelevant. Okay? So you want to go through and all computational constants should be unfolded. And the irrelevant things should be kept. And actually, we want to unfold and reduce, whatever. It's an arbitrary example. Yeah. So when we see a constant, for instance, plus, we want to unfold it and get its normal form. When we see a constant that represents a proof, we just leave it there. So we'd have to go through a term, exactly find the constants in this term, get them from the global environment, check what their type is, and based on their type, do the one thing or the other thing. Good. Now, let me see whether I have the identity function somewhere. Yes, perfect. So a good trick, and you can do this in the exercises as well, is that you start all of this with the identity function on terms, because then you like the recursive identity function that goes through of this, and then you only have to change the one bit of this that we care about. And in this case, it's going to be the bit that deals with the t-const case. Over here, yep. With the t-const case over here, where then we are going to have to find the constant in the global environment and check its type. And we're going to use two interesting things here in order to make this work. So we're going to use a lookup constant function, which takes as input a global environment, a name, and then gives you the body of this constant. And we're going to use a check whether a universe is prop, and then we're going to use the infer type thing here and check whether the universe is prop together. Okay. I'm going to work in a section that fixes the global environment because I need it, and I'm not going to change it. So I work in a section, sigma of type global environment. Good. And now I don't want to call this function identity. I want to call it something like simplify. And I don't have map because I need to do require import list. Cool. All right. Good. And now we only have to change the const case, which is, where is it? Which is here. Good. And again, the description is that if this constant has a computational type, we want to reduce, and it has a non-computational type, we do not want to reduce. So what we have to do is we will have to infer the type in the global context sigma of the tconst cu. The way I wrote infer type, it only accepts closed things that do not depend on any variables. That's why I don't have to pass a local context, but constants cannot contain any variables because they are constants. So this one is fine. So I'm doing this. And now there are two cases. Either this comes back with a result which says, okay, this was actually type checkable with maybe something A here, or it comes back with, let's see what the type of infer type is. It is typing result. Typing result has two constructors, namely check, it worked, or type error, actually this was untyped, which we don't expect to happen. So we can kind of ignore this second case. So let's say whenever we get a type error E, we just return the input again, whatever. But we care only about this thing here. And now I think there are two cases, namely if, yes, if the type that comes back is, wait, let me see what infer type is doing. It is doing exactly what we would like, yes. If the type that comes back is, for instance, a sort, then that what comes back. So if the type of the constant is big type, so a sort, then it's non-computational, and we want to keep it as is. So if it's a sort T, this is more or less the same as type in Coq. So if it's a sort T, we are going to keep it as is. And if it comes back with another thing that is not sort, we are going to, let's call it K. Whatever. If it comes back as K, then we want to look up the constant in the global environment. And if this gives us something where the constant body actually is there, and it's not an axiom, because also in the global environment, that's relevant later. In the global environment, you can either have constants that have a body, those are definitions, or that have no body, those are axioms. If we come back with a constant body that has something, we are going to reduce it because we are not in the, what happened? Yeah, we are in the wrong line again. So let's go back. Yes. Reduce in sigma the whole thing, the whole body. Okay. So if the thing that comes back has type, we just keep it because it's non-computational. If it has any other type, we are for now reducing it. I don't think this is exactly right because we are for now also reducing proofs. But okay, let's keep it like that. For the moment, and expected.
We're using the sum case as well.
Yeah, let me see. No pattern found for this other thing here. Yes, indeed, because actually I didn't give one. So here we just keep the C. Yep. Okay. Good. So we infer if this is a type constant that we see, then we just keep it because it's not computational. If it's anything else, we for now reduce it to the body. And now let's see whether this is actually working. And the section. Now we're going to write the definition. You will see in a second why that is relevant. That takes as input a program, which is exactly what Amin asked about earlier. This is going to be the representation of the whole global context and the term. And what we want to do is we want to run our function simplify with the first and the second projection, because up there it's curried, and down there we'll get it as a pair. And now I think if we do a definition, a constant, this should not be unfolded, and this should be unfolded. 3 + 1 maybe, and simplified. Then we can now run, yeah, I know. We can now run the unquote of running our, how did we call it? Running the unfold computational things program on the result of recursively quoting, and recursively just means also the global environment. Recursively quoting, let's say the pair don't, do. And I would hope that this actually now goes to the pair on the left-hand side. We still have don't. On the right-hand side, we have the number 4. Good. Okay. So that worked. Now let's also follow actually the exercise, because I think if we have a proof here, it's still going to keep the proof. Let's just definition also don't. Let's put the constructor I of truth. And I think also don't. It is now going to unfold this, but we don't want it to unfold because we want to keep propositional constants there. So we will have to change something. Namely, when this comes back with a type, here it's going to be the type true. We have to check whether the type of K is prop. Because if K is a proposition, then we also don't want to unfold. So we want to do two things here. We want to first infer the type of K now. And if this is now going to be T sort some universe, then we check whether this universe is a propositional universe. And if that's the case, then we change nothing. So we still return T const CU because we do not want to change propositional constants. And in the other case, we do exactly what we were doing before. We unfold it, we go on. We unfold it, we go on. Okay, so that's the case where it's this. Let's bind this somewhere so we don't have to write. Let's do something like this. And now here we return the result we were initially attempting. Here we also return the result. And in the type error case, we just return the initial constant. Maybe this is working. No. Ah, but we can seasoned COQ programmer, as you can see. Great. Here. There we go. There we go. Okay. So let's see. And now it's keeping the other constant as well, because it's going to check that also don't has type true and true has type prop. So it's not unfolding because it's going to run into this case here. Okay. Just to show you a little bit what kind of manipulations you can do. Perfect. And now the main exercise you are supposed to do. Actually, I can show you, right?
Yannick, I have a question.
There was a question for Club.
Yeah.
Which
where
completely coincidentally, but that was my plan anyways to let you implement that. So Abhishek asked, very concise, great for an exercise. Is there a way to get print assumptions to output fully qualified names of all items? Print assumptions is the command that checks for axioms, and it only gives you, it doesn't give you the full path to the axiom, it just gives you the name of the axiom. And Abhishek wants to know where the axioms are actually defined and get you the fully qualified thing. And of course, that's not very hard to implement in MetaCoq. So the exercise is exactly this. You're going to write a thing which goes through a term. Whenever it sees a constant, it checks whether this constant has a body. If it has a body, okay, you do recursion on the constant. If it does not have a body, you print out, you add the name to a list that's going to be returned, something like this. So relatively simple. If you want to go more into it, this can be probably made more efficient. But for now, we can do a really simple one, which just does recursion. Now, in order to do that, we have in the MetaCoq repository, MetaCoq organization on GitHub, so github.com/metacoq/tutorials. There's a POPL'24 directory, which has an exercise directory, which has an exercises.b file, which explains exactly what you are supposed to do. Namely, you are supposed to write a print assumptions command that does exactly what I just explained. We are the 4 of us here in the room. This I wanted to do. So before we do that, let's do that. The 4 of us are here in the room because that's the part of the MetaCoq team that is there. I don't think we yet mentioned that this is a thing developed by many people. So the by many people, including Abhishek, who maybe could have known that you can do that in MetaCoq, but whatever. That work on different parts of it. We are here because it was easy to come and because we work on the parts that were mainly work on the parts currently that were explained today. But all right, the exercise is going to be exactly Abhishek's question to implement the print assumptions things, which is in this exercises.v file. The 4 of us, that's where I was going, we'll walk around and we'll help you. Feel free to ask. This can be really interactive. Same for the online people. I don't know how to do that. Maybe we can use breakout rooms or something, but at least we will try to monitor the chat. And if you have questions, either in the Zoom chat or in the dedicated Zulip channel for this, feel free to ask questions. Okay, good. Yeah.
Isn't quoting and unquoting the environment really expensive?
Isn't quoting and unquoting the environment really expensive? And the answer is kind of. It is not horribly expensive, but it's relatively slow. So it's also not relatively fast. So for this exercise, it's going to work because we're not going to do big things. If you are working on big things, just quoting the environment once is also not horribly expensive. We can do it on reasonable terms. The environment is only going to contain constants that actually appear in the term. So the quoting is going to drop things that you don't care about. You're not going to quote everything that's currently defined in Coq. I think there was a paper at maybe something like ITP 2018 by Jason and Adam and other people that compared a bit different ways of doing reflection and reification. And I think still MetaCoq's way of quoting and reifying is faster than any other way because essentially it's the identity. So yes, it is expensive and you only want to do it once and then work on this environment, but you can write also efficient procedures on this environment and it's kind of working. So for this exercise, nothing should be efficient. It can be horribly slow, don't worry. But in general, things can be made efficient. We also have a way to write the MetaCoq plugin in Coq, then extract it to OCaml and natively plug it with the kernel, where you don't even have to quote anymore. But okay, that's a bit too much for today. Cool. All right. Then we can start with the exercises.
Context representation in MetaCoq is represented as a list because that's very easy to do. But in the actual Coq implementation, it's of course not a list. Yeah, so I mean, like the actual data type is smarter and like the bulk filtering stuff happens on reasonable data types. Yeah. And it's just easier for us to manipulate things with lists in Coq. So that's what you get at the end of the day. But the things down there are less negative.
Good. All right, but try to get the exercises file, try to get it set up, and then just start. Shout if you have any questions. All right, and I again cannot stop sharing. What reference? I can produce one. Yeah, I think I'm only sharing. You can see what. Yeah, I know. But that's just because something is off figure. It doesn't matter. Doesn't matter. I guess the online people did not actually see the list of project members, but whatever. Yeah, it doesn't. It's not so bad.
My degree is only on the record, right? What is already the record? The live coding.
Yeah, I think so. Actually, that was not on purpose, but
Yannick, you're muted.
Like doing like lift and we done by hand, which can take up very long, very fast. It's not like everything is very reliable.
Especially agree.
That's very simple, to, like group the case, you have all the circle there, but also sometimes you have higher representations. So I mean, it's a no, so you probably want to do unset long term. Oh yes, it's still not done. What?
Yeah, you can try. I think this can't guess the frequency. Yeah, try to say about to try the attribute.
Yes, that's very. Just what happened in the structure? Maybe it's unhappy about. Yeah, okay, so if we're not able to get it because we're doing the things, but if you say what it should be, it's not checking it anymore. So you need to say what in principle.
Just look up constant variance, which just look up and possibility structure.
Okay. Do you want to say it or?
No, yeah, I thought you could say it.
Okay.
Once I have.
I have my adapter as well. Oh, okay, that's even. Actually, that's what I was also using lookup constants.
Implement what's the words, but then you can start the elective base.
Okay, yeah. Yeah, so it's fine to put the solutions online, right? I mean, I already said we would do it. I already said we would do it, but
Unless you want to use it as an exercise.
do you want to?
Do we have solutions?
Well, I wrote.
Perfect.
Because
no, I have one
okay,
as well.
Good.
Yeah.
See, we're very
Question?
dedicated.
No.
Didn't
You have a
just
question?
Didn't do that in the training yesterday.
Small remember question.
Right.
Copy pasting identity each
Mm.
time.
Mhm.
It would be easier to have a generate map function.
So yeah, I mean, I guess fold might be even make sense, right? Because map, it's not clear what you would like to map inside the term.
That's the power and both the purpose.
Okay, but that's not, for instance, the print assumption.
You're just passing the time level and then you just do all the changes and identity in that. You use that something.
Yeah. But I mean, for print assumptions, for instance, you do not produce a term, so it's not a map, it's a fold. Yeah. But yeah, in principle, yes. No, yeah, Dominique dit, bah, désolé, je dois y aller. Du coup, bah, Lucas a fait, ok, salut. Et puis,
Ah. Mais il est motivé, Lucas, il est comme de ouf, je le sens.
Lucas?
Ouais.
Mais il a l'air motivé pour tout.
Ouais, mais en fait, mais
Je l'ai mis.
il était à Cambridge. Et je vous dis ça, il est parti à. Maintenant, il est à Oxford, je crois.
Ok.
Mais il était à Cambridge. En fait, genre, il vient enfin, il a fait plein de trucs, mais quand il était à Cambridge, c'est des trucs de certification, de genre protocole de vote, et tout comme ça.
Ok.
Mais je crois qu'il était un peu tout seul à faire du code. Et du coup, il était trop content que je sois là, il me posait plein de questions. J'arrivais régulièrement, il venait toquer maintenant, genre, j'ai une question. Et mais oui, il est très motivé pour apprendre des trucs. Et c'est genre, ah, c'est trop bien, c'est comme ça que ça marche.
Ouais. Mais ça doit être, il n'y a que lui et Abhishek qui utilisent la
Ouais.
MetaCoq Club maintenant.
Mais je pense que.
So, yep.
You told us during the talk that we should use most app.
Make apps. Did you say that? Okay, yeah. Okay, well.
And then the exercise we always use.
That's true. So so make app is the one that preserves the invariant, that you do not have nested applications. So indeed, if you're not sure that your program is going to preserve that invariant, then you just use make apps, and that's equivalent. So I guess it's just the safest way to write a T app. Sorry? Oui, c'est ça.
If you figure it out and you could write a nice explanation about it, we would appreciate it.
You're answering, Meven?
I'm quite.
To Mario? No, no. Yes. Equals quote and quote. What are you trying to say? It's called mouth, I think. Let me check.
Okay. Yeah.
Yeah, I think we don't have a way to, like in LTAC, you can put it in quotes, say unfold in quotes star, and it would work. But in MetaCoq, we don't have that, but that would be nice, yeah.
I'm very interested in that type of program.
That's sort of the exercise.
But I decided not, so I think it was about just meeting. So very great. By the jumping.
I don't use it.
You know. Why not?
Not anymore, but
Because most things you can do purely and it's nice. You need it sometimes to do definitions and stuff like this.
Yeah, but usually you write most of the core thing.
I mean, it's supposed to be blue code, essentially.
Yeah.
No, but you can also,
You could do LTAC-ish things in there, right?
for instance, you could, even this, you could, the print assumptions, you could also write by traversing and then doing the print when you encounter an axis.
So also we had the question that since you have the sigma and that could break gives you the minimal sigma, maybe you don't have to look at the terms in the print assumption.
Sure.
You could just traverse the sigma. No, because you still need to recursively. I know, because the sigma contains everything that's recursively dependent. Okay, so, yeah, so you just go through sigma, look at the thing that have nobody, and
That's it.
and that's it.
It's actually much simpler.
Well,
For the exercise.
well, I mean, it's that means that the creative student has found has understood very well what's happening, and they are
Maybe we
able to
should
find
put it in the
creative
solution file though. No?
Yeah, as an alternative way to
solution.
do it.
Yeah.
No, but it's you still see at least the entities that are not completely not.
But then you see what.
Is there a more exciting way to traverse through inductives, or is this kind of like what you have to do in pattern match?
So which thing are you defining? It's the print assumption.
Yeah,
Okay, so basically what I did is I just assume that if you give me an inductive type, then it's not using axioms.
I see, but in practice, it could use axioms because
Right, because you could mention them in the
Right.
constructors.
yeah, or you can mention them in either the constructors or the arguments.
Yes,
So
that's true.
I have been
Right.
so like having that does add it. Oh,
Yep.
well, yeah,
Yep.
it's fine. That does collect this axiom. So if
Mm.
I do this, it does do that. But I'm assuming for all of it, I need to also add it for like either it could appear in the index or also the body of the constructors, blah blah blah.
Right.
Yeah. So I was wondering if there was a saner way to like if it must be just traversable.
Yeah, I think so one solution that was also mentioned is that since you have the sigma, you can just traverse the sigma and look for axioms in that and
Mhm.
don't have to look at the term. That might be the easiest way.
I
Because
see. Well,
but indeed this is a bit painful, and I guess we have some I don't know if we have facilities to
traverse terms.
yeah.
like, because she's looking at the inductive case in case they like
Yeah,
indexes
right, indices or anything else could
Ah,
technically
yes.
refer to axioms.
Yeah,
so
that might, I think.
yeah.
I think all of us just ignored the
Okay.
yeah.
Okay. Yeah, I was wondering, because I mean, I imagine you could just define a traversable and then.
Yeah, so
Right,
we
yeah.
don't have a lot of like support for fancier.
I mean, but this,
traversals and thing, and probably if wanted to be like do some more real things.
Is there a type class somewhere traversable, or what would you do?
Well, I don't know if is it available in Coq standard library, but I mean, I imagine you could just define a traversable type class and then like.
Is there some type really Coq that already has it?
SDPP might have.
I don't know.
Yeah, SCDPP might have it. I haven't used it in Coq for sure, so.
We'll have to check, but yeah, I mean, we probably want this kind of infrastructure to make it a bit less terrible.
So-
I can make a list because I have the student whose job it is to do.
Oh, yes, then
Yeah.
probably, yeah.
Yeah. I mean,
I have a
I've
student whose job it is to do all of these things.
Excellent.
I've seen it in projects, but not like a general library. Oh, yeah.
It's the typical state of things in conservation. You have the same stuff in 3 different purposes, and pretty much the same thing, more or less, maybe not exactly.
If only there was already a library that does this, and then it's like,
Yeah.
Yeah.
Actually, there's more of them. One is universally polymorphic, one is not maintained.
Yeah. Yeah, and then you import it and you're like, oh, universal consistency, and it's like, oh, yeah.
I guess I'm just going to copy paste it.
Yeah.
The keywords, and it's the best way.
Yeah.
Standard structure. It's called this vibrant community, rich ecosystem.
whether or not it's portable or.
Well, that's a different question.
Yeah.
I think that each and amount will run into enough problems. So.
But is there a reason why the inductive, it has both, when you, after the result of lookup inductive, that result has both a mutual inductive body and a one inductive body? What is the?
So yes, so I think
Yeah.
when you look up an inductive, it gives you the full mutual definition of everything,
Uh-huh.
and then it gives you in this mutual thing the body of the one inductive you're looking at.
So if you have even
I
odd,
see,
you print
right, right.
odd, it's going to say it's part of the even and odd mutual definition, and also like
Here's
here are
the
the
odd.
constructors for odd because that's the one you asked for.
I see,
Yeah.
okay.
I think that's what's happening.
Cool. Mm.
Yes, once I'm starting screen sharing.
Right, but I guess another way to represent it, like, I guess you could always have, no, mutual inductive body, and then the other could just be an indexing into that thing, but.
Yeah, that
some-
might as well be the. I guess it's just for like because this is an active, so it's easy if you want to directly go into the one inductive, that you don't need to do some fancier things. But,
Right, right, yeah. And I was also curious, so it seems like in the template monad, there's like different versions of either there's the optimized version or the non-optimized version for the bind. Is there actually a difference in performance and which one?
So I think
You have to ask
one is, isn't it that one is deficient in coq and the other one it's extracted?
What? I
No.
don't know. We have a bind opt and we have a bind not.
Yeah, like the typical like flattening of the bind optimization. This looks like it just represents the normal form for bind and.
Right.
Yeah, I tried to do it in very simple examples and I couldn't see the difference in performance.
Yeah,
so,
I never
yeah.
used this. I don't know who contributed that.
Yeah, okay.
The TM optimized bind.
I think it's Gregory, no? Or Jason? Jason.
Yeah.
okay.
Okay.
Yeah.
So
Yeah,
they have
I mean,
very
it
specific
might-
use case
Yeah,
that we don't know anything about.
Jason started a project of trying to show things like log theorem, so that they do like probability thing, and so he started like quoting every single bit of MetaCoq as MetaCoq.
I don't know. What
Okay.
is-
So I think his goal was to get like the
Like
the typing
abstract-
relation,
Yeah.
like represent, like gets the term ASC for the typing relation of MetaCoq in MetaCoq itself.
Okay.
The kind of the first step of this like arithmetization thing. And so I guess he developed a lot of infrastructure for quoting a lot of things. And
I see.
stuff like that,
Right.
so it might come from this kind of project.
Yes.
Okay, cool.
And then you will have to assume that he has a reasonable pattern. I don't know. We probably should have time.
So, on the things that are currently not supported, there was modules, but it supports type classes.
So I think, I guess it depends what you mean in terms of support.
Mhm.
What's sure is that currently, like, Pickwick, or it's does not, you know, like, there's no typing for modules or something like that.
Okay,
But there might still be representations on the template side of these things. It's just that, like, you could manipulate them, but
Not type classes.
Not, well, they're just.
Because type classes are not, no, they're not modules. Type classes are just, they're part of another layer, so they're not in at all in the kernel.
Yeah, I mean, you have records which are what's used to implement type classes, but I guess.
Yeah, but you
Type
don't.
class system is on the elaboration layer.
oh, I see, so it's not even.
So it's not even in
okay,
here
yeah,
probably.
Yeah.
So I guess you can still, because the template monad can call the checkers,
yeah. Mhm.
so you can also call like elaboration and it's gonna try and solve these things.
Right,
But here it's like everything's fully elaborated and so no unification, no type class search, no nothing.
sure, yeah. So I don't know, I don't understand much of the clock internals, but like sometimes I also run into problems where clock user, I try to process QED and the QED doesn't terminate sometimes.
Mm-hmm.
What does
Yes.
that, okay, so like, for example, I ran into this problem when I was trying to input like a explicit measure for a certain kind of fixed point, and I think when I was trying to use like program fixed point doing this, and I tried to QED, the proof of like measure is going to decrease somehow. When I tried to process the QED, it wouldn't terminate.
Mm-hmm.
Is there which part does that feedback correspond to? Like,
Usually, if the QED is slow, it's due to conversion taking ages. But you should not have too much. I mean, it depends on your actual.
Okay.
Yeah.
right, yeah.
Sometimes you need to make some things opaque because conversion will take a wrong path and it might and apparently diverge. It's not diverging.
Yeah.
But it might just blow up your memory.
Right. Yeah, I don't have the example just right now. But
Yeah, usually you need to give hints, opaque hints to say, don't try to control this.
oh yeah, I don't know if we've actually met before.
Not virtually, yeah.
Yeah, virtually we've chatted before. But yeah, hello,
Hi.
I'm Irene, Steve, and you're Matthieu and
Theo,
Theo,
yeah. I think we met in Ljubljana.
Ah, yeah, ICFP last year. Yeah.
Yeah, yeah, yeah.
You have to know pretend that it's that's right.
Question by Tadej about how JSON gross stuff is progressing. It's not?
No.
Okay.
Somebody wants to take over. That's in the Bulgaria. No, yeah, is that the same as pending? It's just about.
I don't know where, like when I do.
In what compare?
It doesn't, like when I do locate per pair, it doesn't know about it.
Can you do a good prep out there?
Okay. Time's up. Yep. So thank you, everyone. We're going to put the solutions online. You can keep asking questions on the lib.
Or during the week.
Or during the week, yeah, of course, yes. And after you have Zulip. But yeah, we're happy to answer your questions. Always.
What's that? Is there no shipping?
Yeah.
So Theo's say hi to you.
Oh.
Typical man. And we just shared his in the office actually.
Nice. What do you work on?
So working for thoughts of more in the application side, so using processors, controllers, and all that. Hardware.
And you're attending also because the workshops that are related, or you just.
I'm actually just for tutorials.
Really?
Yeah, actually, I came for.
You sent me. And then you said you might be.
So actually, straight and kind of. Yeah. And it's nice to see faces.
Yes, see the people online, it's.
The best place to see faces is every summer the POP users on developers. Which is one thing, where you all of the developers, lots of users, and there's nothing in session. So it's, when you can say it's an academic event, so you know that
And Theo knows about this.
and Theo knows about it, yeah, right. Yeah, sure. Yeah, Theo because Theo goes.
Yeah. And you know, when works maybe.
No.
Usually it's summer-ish, spring.
But it depends a bit on like yeah.
Often you see in Sofia, right?
No, but yes, but that's only because if we don't organize anything until 1 week before, Sophia says like, okay, we can do it. Is this day tomorrow?
Yeah, tomorrow, then I leave tomorrow. Oh, it's wrong.
So you're right.
Yeah.
I'm gonna make it to